I want to talk about one of my favorite techniques in multivariable calculus, the method of Lagrange multipliers. Lagrange multipliers is a neat little trick, a neat little set of techniques that they don't get a lot of coverage in typical multivariable calculus classes. A lot of times classes will either leave this topic out or brush over it so quickly that people have no idea what's going on. So what I want to do is work through an example of Lagrange multipliers in action to try to point out the features that make it an interesting and useful technique. I've also got a whole web page talking about this, an introduction to Lagrange multipliers in a sort of conceptual way. Hopefully they'll complement each other. This is a specific example that gives a lot of conceptual sort of background of the method. But so, okay, what do we do in calculus, especially differential calculus? A lot of what we're doing is optimization problems. We want to find the maximum or the minimum of some function. Those are the things we're looking for. So here's my example. I'm a very visual person. I like to think in terms of pictures. I like to have things that I can really draw on a board or something to really see what's going on. So visual, intuitive things, distance. I want to find what point on the xy plane, what point xy is closest to the origin. Or in other words, I want to minimize the distance to the origin. Distance would be square root of x squared plus y squared, except I'm a physicist, so I'm lazy, and I don't like square roots. So instead of minimize the distance, I'm going to minimize distance squared, x squared plus y squared, and you can prove to yourself that minimizing distance squared is the same as minimizing distance because distance itself is never negative, so blah, blah, blah. Anyway, this is safe to do. I want to minimize this function. Okay, that's actually a really boring question. The point closest to the origin is the origin, and we don't need any sort of methods to tell us that. That's just something we know. But here's where Lagrange multipliers come in. I don't just want to ask this question. I want to ask this question subject to a constraint. The constraint is that the point I'm interested in has to lie along the curve y equals x squared plus 7/3 x minus 1, a parabola. So I've now said, hey, I've got a parabola in the xy plane. I want to know what point of that parabola is closest to the origin. I've drawn a cheap little sketch here, but maybe I will magically make the video show you a more zoomed in, pretty version from a computer. If you look at the sketch here, you will find that you can pretty much eyeball where that closest point is. It's a little bit to the right of the origin. It's maybe a tiny bit below y equals 0, a tiny bit below, sort of down to the right and a tiny bit down from the origin. It's very close there. That's going to be the closest point to that curve gets to the origin. How do I find that specific point? Okay, well, there's actually multiple ways of doing that, and I'm going to start by talking about the simple brute force way, because it's better to know what you're comparing Lagrange multipliers to. So if I wanted to brute force this, I would say 2 dimensions, I've got x and y, 2 variables to worry about here. I'm trying to minimize this function, but there's a relationship between x and y. So I can just plug this in. My brute force method is just to plug in d equals x squared plus y squared. Well, I know what y is in terms of x. So x squared plus 7/3 x minus 1 squared. I've got this big equation. You can tell that it's going to be quartic. It's got an x to the 4th power as its highest power. And I'll do that. I plug that in. Now I have a function of one variable. And to find maxima and minima, well, local maxima and minima of that, I just set d prime of x, the derivative of d with respect to x, equal to 0. And what will that be? I'm not going to go through all the ins and outs of the calculation I need to do to get this. You can do it yourself. Algebra, you have fun. You can multiply this out, expand this, take the derivative, and we'll set that equal to 0. That will give me local maxima and minima. And that's one way of solving this problem. And for this particular problem, that's a perfectly fine way of doing it. It seems, it's very reasonable. We've gotten down to a single variable calculus, and that's an easy thing to do. Yay. In fact, we can even look at this. I want to go ahead and show you this just for intuition. Show you a graph. Well, we've got this graph here. I'm going to put up the graph on the computer, and we've got the old graph, but now overlaid on this. I'm going to show you. You can see here, there's a graph of the function itself, of this distance function, distance to the origin at each point. That's just overlaid on top of the parabola that was already there. And you can see where that minimum is. And the minimum of that new function overlaid there does seem to match up pretty darn well with where your eyeball would say that's the closest point. There are a couple other interesting features of this function, distance function, that you might notice, by the way. There's a local maximum somewhere in the middle, and obviously on the two ends the parabola gets infinitely far away from this thing, from the origin. But there is a place where it gets, as you're coming in, it gets closer and closer. If you come in from the right, it gets closer and closer down to a minimum. Then going farther left, it goes up to a local maximum, a little bump, and then a little local minimum, and then off to infinity. So all those points could be interesting to find out about for one purpose or another. We're mostly interested in the closest approach, but keep in mind all of those are interesting points to worry about. Okay, so this was our brute force approach, and you can see it's pretty straightforward. We don't need Lagrange multipliers for this problem, but we can use it to help us see how they're going to work. So that's all I want to say about brute force. Now I'm going to throw it out, because that's not what we care about right now. What I want to do is use this to illustrate Lagrange multipliers. And so for that, I need to tell you the idea behind the method of Lagrange multipliers. And it's actually a pretty slick idea. It's kind of cool. The idea is that visually, again, I'm a very visual person, visually, this distance function, I can think of distance as something that gets bigger and bigger and bigger the farther you get from the origin. The farther I get from the origin, the greater my distance is. In particular, if I just draw a bunch of concentric circles around the origin, here's a little circle and a bigger circle and a bigger circle and a bigger circle. If I look at concentric circles going farther and farther out, centered on the origin, that corresponds to increasing distance from the origin. So in particular, the very first circle that touches that parabola is going to be the one whose radius is the distance I care about. And the point where it touches is going to be the point where the parabola comes closest to the origin. Hopefully that's intuitively clear. Again, this is why I like the visual examples for first learning about Lagrange multipliers. Hopefully that's clear. Now here's the really cool, sneaky bit about this. If you look at the way this works, think about the direction, maybe think of it as the slope of the parabola at that point, and the slope of the circle at that point. At the place where they touch, those match perfectly. The slopes match up. They're just completely touching. It's great. So in particular, another way of thinking about this in multivariable calculus, since we have that multivariable calculus tool available to us, we can say, in what direction is this function increasing the fastest? And well, we know that the distance function is increasing straight away from the origin. That's little arrows perpendicular to the circles that we're drawing. And so in this circle, the first circle that touched, we've got that distance increasing away from the origin everywhere we go. And the other neat thing is that if you look at the parabola itself, you can also think of that as something that has a distance, that has a function value increasing from one side to the other. If, in fact, what I want to do is introduce a function that is increasing that happens to be 0 right where that parabola lives. So I'm going to take this function form here, and I'm going to write it as a more general constraint function. Let's see. I'm going to write this as a constraint function. I'm going to call it g as a function of x and y, and it's going to just be x squared plus 7/3 x minus 1 minus y equals 0. That's my constraint function. I've just rearranged this thing and set it equal to 0. I've put all the stuff on one side, set it equal to 0, and called that a function, g of x and y. The neat thing is that this function equaling 0 over there, that's my constraint, that tells me that that's something that's going to, at least in general, increase from one side of the parabola to the other. It's going to be, I don't even know which side is negative. I guess negative on this side, positive on that side. So the g of xy equals 0 is my parabola, corresponds to my parabola, just rearranging my original constraint. And this function, the value of that function, is getting bigger as I move out of the parabola. In particular, this function gets bigger. My g of xy increases that way. As I move out from the parabola, that's the increasing direction. And that sort of makes sense, right? Moving along the parabola, you're staying exactly at g of x and y equals 0. That's the whole point of the parabola. As I move away from the parabola, as I go perpendicular to it, that's where g of x and y is increasing. So okay, here's the neat trick that we get to use. Remember we said the slopes of the circle and the parabola matched at that point? Well, hey, these directions of fastest increase are perpendicular to the slope. They're perpendicular to those curves, and so they match. At that one happy magical point where the parabola touches where the circle touches the parabola for the first time, at that one minimum distance point, those two arrows are going to point the same way. They have the same direction. They probably have totally different magnitudes because we haven't made any effort to make the magnitudes match up, but they're going to point the same way. So in particular, how do I find the direction in which function is increasing the fastest? That's the whole point of the gradient. The gradient of my distance squared function, d, tells me the direction and magnitude of those little brown arrows that I've drawn here, of the increase in distance. And that has to equal the direction of the increase in g. Again, gradient of g will tell me what is perpendicular to my parabola at any point on the parabola. So setting those two equal is almost what I want to do, but remember, I don't care about magnitudes matching. All I care about is directions matching, because I can change the magnitude of this just by multiplying my g of x by 2, and that won't change anything. So I need some sort of function, some scalar function to multiply gradient of g to set it equal to sort of absorb any differences in magnitude. And so this is going to be a function lambda of x and y times that gradient of g. So lambda here is a scalar function, not a vector, and it is the Lagrange multiplier. That function is just the scalar piece that that corrects for the difference in length between these two vectors while leaving their directions forced to match. So this is our equation our vector equation that relates these two things. And now let's figure out what it tells us. This is a vector equation, so I can translate it into a pair of scalar equations. That means first thing I got to do is actually write out what my scalar equations, what my two vectors will be. Gradient of d, I don't know what notation everyone else in the world uses for this, but I'm going to use x hat, y hat notation for my vectors. So gradient of d, gradient of this thing, well, the partial with respect to x, that's 2x x hat plus partial with respect to y, 2y y hat. That's my gradient of my distance function, of my goal function. And then my gradient of g, gradient of my constraint function, I can do that. My x partial derivative gives me 2x plus 7/3. That's my x hat part. And my partial with respect to y gives me minus y hat. So there we have it. That's my gradient of d and gradient of g. Those are my two normal to the curve, my two sets of arrows, my two vector fields perpendicular to these curves. And I want them to match up. I want to set them equal up to some scalar multiplier, my Lagrange multiplier. All right, well, we already know what the problem is, so I can erase all this stuff. We know what the problem is. We can do this. And so let's set these equal. Let's set the x components equal in this equation and the y components equal. X components, I get 2x equals lambda of x and y, but I'm not going to write the of x and y every time because you're smart. Lambda times 2x plus 7/3. And then for my y component, I've got 2y on the left equals lambda times minus 1, because that's the coefficient of my y hat over there. And okay, look, I've got two equations in 3 unknowns. I once got stumped on an exam at this point. I had 2 equations and 3 unknowns, and that's not enough to find solutions, to find specific solutions to a system of equations. I'm a physicist. Anything when we have 3 equations and 3 unknowns, or 8 equations or 8 unknowns, I assume that's good. I'm not going to worry about degenerate cases, even though those are important if you're being a mathy person. But so, okay, we've got these things. There is 1/3 equation we get, and it's our original constraint. I still have y equals x squared plus 7/3 x minus 1. That's my third equation. That's 3 equations and 3 unknowns. And right now, as I told my physics students, the physics is done, or in this case, the hard part of the math is done. This has now become a simple algebra problem to find those values of x and y that make this work. So how would I do this? Let me sketch it. I'm not going to do all the algebra in front of you. I guess first I'd eliminate lambda, since that's just some pointless little multiplier in to make this process work. So this tells me that lambda equals minus 2y. Okay, so now I can eliminate lambda from this equation. That means, putting those together, that 2x equals minus 2y times 2x plus 7/3. Well, okay, reflex action, I have to cancel out those two 2's because it's easy to divide both sides by 2. Now I have an equation already ready-made to plug in y. So I can take that, I can pull this in there, and I can say x equals x squared plus 7/3 x minus 1 times 2x plus 7/3. And if you look at this, I can multiply it all out. It's a cubic equation, right? X squared times x will give me a cubic as my x to the third is my highest term. It's a cubic equation. I can bring this x back over, put it all together, solve it using standard algebra tricks. Probably, if you're, if you're lazy like me, that's going to mean plugging it into a computer or something. Just any sort of computer algebra system can solve a simple cubic like this and give you some answers, at least numerically. If you're really clever about factoring and all this, I'll go ahead and tell you what the numbers come out to be. If you're really clever here and you put this all together, you'll find that this whole thing, when I bring that x over and everything, I will get the equation 0 equals, just copying down my math from earlier, 2x cubed plus 7x squared plus 49th x minus 7/3. That's the cubic equation that you wind up with. Check me at home, kids. That's the cubic equation you end up with. And if you're a really sneaky person with factoring and you're good at this stuff, you might even be able to spot that this factors, and that this is equal to, still 0 equals, is going to equal x plus 7/3, 2x plus 3, x minus 1/3. So in other words, my 3 points, once I plug, this tells me my 3 x values. I can plug those back into my constraint to find my 3 y values, and I'm set. My 3 points end up being minus 7/3 minus 1, minus 3 halves, and minus 9/4, and finally 1/3 minus 1/9 are my 3 points that I come up with. Cubic equation in general has 3 solutions. We happen to have lucked into having 3 real solutions here. That didn't have to happen. And in fact, we lucked into getting 3 rational solutions. I had fun coming up with an example that would do that. So we've got this, and okay, things to comment on in this set of things. First of all, looking at this list, it's immediately obvious that the only one of these that has that's going to be smaller than 1 is this one. That's going to be my closest point. And if you were really eager, you could plug in the distances in Pythagorean theorem and find what the distance is. But that's clearly going to be the closest point. And hey, let's look back at our picture, at the drawing we had. I'm going to bring one up that has actually 3 circles in it, showing circles doing each one of these things. And let's look at where our closest point was. And hey, look at that. Right where we thought it was by I, that is x equals 1/3, y equals minus 1/9, is indeed that point of closest approach. That's where that smallest circle touches the parabola that was our constraint. And then if you look, the other 2 answers we got are meaningful as well. You can see that the largest circle that is drawn in this picture will give a local maximum, not a global maximum, because you could go infinitely far in plus x or minus x and get farther and farther away, but a local maximum. That's this middle point here, and then farthest to the left at x equals minus 7/3, y equals minus 1, you'll see there's a local minimum as well. It gets a little bit closer before it toodles off to infinity. So we've got all three of those points showing up as part of our as solutions to this equation. And that's how we've used Lagrange multipliers to find that point of closest approach. Hopefully that gets most of what we need to talk of what you'd want to talk about here. Obviously, this doesn't very obviously does not avoid the need to assess each one of these points that comes up in the equation, because as you saw, some of those are local maxima, some of them are local minima, not global minima. You have to assess them. You have to find some other way of figuring out which one's what you really want. But at the very least, you can use these as a guide to this. This is the same sort of starting point as you would have gotten using other methods. All right, so what did we gain by doing Lagrange multipliers here? Well, so I'll admit it, this equation we got at the end of the Lagrange multiplier stuff down here, this equation is the exact same equation you would have gotten if you'd done the brute force method I talked about at the very beginning. If we'd just gone through, plugged in the y equals to my distance equation and taken a derivative, plugging in that y equals would have given us a quartic, sum x to the fourth term, derivative gives us an x cubed. So there's not actually a savings for this particular problem. It got to the same point. In fact, you can prove that it must get to the same point that either way, because it's math, it has to work. But what did we gain? Let me tell you why this is nice for generalizing to other problems. We never had to worry in doing Lagrange multipliers. We never had to worry about doing some precise parameterization of how we're going to parameterize things. We never had to say, oh, I have to express my distance function of x and y as just a function of x instead. We never had to do that. We were able to avoid having to go to a specific parameterization. Sometimes it can be a real pain. This is easy, y equals thing, I can plug in for y. But in more complicated examples, it can be a real pain to solve this, to give you a y equals function of x and then plug that in. Or if it was a circle I was looking at as my constraint, or an oval, instead of a parabola, it would have been x squared and y squared. I'd have to do it twice. I'd have to do the whole problem once for a positive square root, once for a negative square root. So there are a lot of things like that that are made easier just by doing this kind of problem, and not but just by setting up a parameterization, setting up a problem in a way that doesn't require you to find a parameterization. Setting up something where you can just take the constraint function and take a gradient of it without having to solve it first. Basically, we're doing the derivatives before we try to solve the equation rather than after. And sometimes that can make all the difference in the world to make something solvable, to make it a manageable problem. Hopefully that's giving you at least an idea of how Lagrange multipliers work. It's all about finding those places where the two curves touch, where the curve of what you're trying to maximize or minimize or whatever just barely touches the constraint surface, the constraint curve that you're putting in. And where those barely touch, there you have it. That'll tell you those points, like we saw those three circles, those points are the points where you'll find local maxima and minima, and you can assess from there. I love Lagrange multipliers. They're a neat little trick, they're a neat method, and I hope that this gives you at least an idea of how to use them yourself.